Hello everyone, we are Group 7 from CSD2183, and today we'll be presenting our project about spatial hash grid for efficient collision detection. I'm Alyssa and my group consists of Ting and Mingyu. Our aim is to showcase why brute force collision checking becomes slow, and how spatial hash grid dramatically improves performance. Here is the problem that we have identified, is that collision detection gets extremely expensive when you have too many objects. The brute force method compares every object against every other object, which is O(n) squared. So when n gets large, the number of collision checks explodes and everything slows down. So this is the core problem that we are trying to solve. Now, we will introduce to you the spatial hash grid, and it is able to solve this issue by dividing the world into grid cells. Each object is placed into a cell based on its position. Instead of checking collisions with all of the objects, we only check with objects in the same cell or neighboring cells. This reduces collision checks from O(n) squared to roughly O(n) on average. It's fast and simple to update every frame. So the reason why we decided to use a spatial hash grid is because it dramatically reduces collision checks. It avoids expensive brute force O(n) squared comparisons and focuses only on nearby objects. This gives smoother performances when many entities are on the screen. It's also much simpler to implement than tree structures like quad tree. And it also works really well for fast-moving objects where we rebuild the grid every frame. In our application, the object moves every frame. For each frame, we insert every object into spatial hash grids. Then, collisions are checked only within the local cells. We also have two modes, the spatial hash and brute force, so you can directly compare their performances. The application also visualizes the hash table, including how chaining works and how chain length grows under heavy load, which now we will be showcasing the demo of our application. Now, I'll show how our application visualizes a spatial hash grid and how the hash table behind it works. We have implemented the DIM GUI to allow real-time visualization with different values and checks. Currently, we're in the spatial hash mode. Each circle is an object, and the grid you see is the hash grid. Every object is placed into one or more grid cells, and those cells are stored in a hash table. Each cell in the grid maps to a hash table bucket. Inside that bucket, we use separate chaining, meaning each bucket holds a list of objects that fall into that cell. Chaining is simple to manage because objects can freely enter or leave cells every frame. For example, this cell right here has about 4 or 5 objects, so the bucket for this cell has a chain length of 4 or 5. Collision detection only happens between objects inside the same cell or neighboring cells. You can see the collision count here. This number stays low because we're only checking local neighbors, not everything on the screen. When I increase the object count, notice how the collision checks grow slowly. This shows the O(n) average behavior of spatial hashing. Now, I'll switch to brute force. Notice how the collision checks immediately shoot up? That's because brute force compares every object with every other object, O(n) squared. This is exactly why brute force becomes unusable with many objects. Spatial hashing isn't perfect. If the cell size is too big, many objects fall into the same cell. Now look, the collision checks goes up and the system starts behaving closer to brute force. This is called degeneration. When most objects land in one or two cells, the hash table creates very long chains. So tuning the cell size correctly is important. If I bring the cell size back down, the chain shrinks and collision checks drops again. This shows how data structure recovers when the load is balanced. So overall, the application demonstrates how our spatial hash grid is implemented, how chaining is used to store objects inside the hash table buckets, and why this approach is much faster than brute force, and how poor parameters can cause degeneration. Everything on the screen, the grid, the cells, the collision statistics, is here to help visualize this theory.
Comparing the performance of the two different approaches to collision detection, the brute force method checks every possible pair of objects, which means its complexity grows as big O of n squared. In practice, once we exceed around 300 objects, the system slows down significantly because the number of checks explodes. In contrast with the spatial hash methods, by dividing space into a grid and only checking objects within the same or neighboring cells, we reduce the average complexity to big O of n. This keeps performance smooth even as the number of objects scales up. With brute force, performance quickly degrades, while spatial hashing maintains efficiency and responsiveness. This explains why spatial hashing is the preferred solution for real-time applications where a large number of objects interact. Of course, implementing this wasn't straightforward. The first challenge was understanding spatial partitioning. Conceptually, it sounds simple. Divide space into cells. But in practice, deciding how to partition efficiently required careful thought and experimentation. Next, we had to tackle choosing the right cell size. This was one of the most critical design decisions. If the cells were too small, we ended up with excessive overhead and too many empty cells. If they were too large, collisions weren't detected accurately. Finding the sweet spot taught us the importance of balancing precision with performance. We've also encountered movement in collision bugs. Objects moving across cell boundaries sometimes weren't updated correctly, leading to missed or duplicated collision checks. Debugging these issues gave us deeper insights into how dynamic data structures behave in real-time systems. Finally, debugging and performance testing was a major learning experience. We had to validate not just correctness, but also scalability. Stress testing the grid with thousands of objects helped us confirm that the spatial hash grid truly outperformed brute force methods. Overall, these challenges push us to think critically about design trade-off, debugging strategies, and performance optimization. They were tough, but they made our implementation stronger and more reliable. Despite the difficulties, the results speak for themselves. Our project showed that the spatial hash grid provides a significant performance boost compared to brute force methods. By organizing space intelligently, we reduce collision checks from quadratic complexity to near linear behavior, which makes a huge difference as the number of objects grows. We've also demonstrated this improvement through our application, where the system stayed smooth and responsive even under heavy load. Seeing this efficiency in real time really highlighted the practical benefits of this approach. Finally, beyond performance, this project gave us a stronger understanding of algorithms and data structures. Implementing the spatial hash grid challenged us to think critically about design trade-offs, debugging, and scalability. Thank you.